Friends, hello everyone. We're glad to be with you again. So today we're here in the AERONOVA studio with the chief designer of microturbine type power units, Andrey Kostyukov. Andrey Veniaminovich, hi.
Good afternoon, dear viewers.
Yes, so today we'll get into the details and talk about the history of microturbines in general. What they are, when they appeared, where they are now, and what the future holds. We'll get to know Andrey Veniaminovich a bit better, and we'll also discuss the applications of those very microturbines in aviation and elsewhere. Andrey Veniaminovich, whenever I look at microturbines, and in the past I was very closely tied to space engines, I realize this is the summit, truly the highest mastery of engineering work, of design work. And you, as a bearer of this knowledge, tell us where they hand it out, how you acquire it, where you obtain it.
I beg your pardon, Fyodor. Do you obtain knowledge or microturbines?
Knowledge. What's your education?
My education is a technical one, specifically in turbines. My education is from Moscow Polytechnic University, the Department of Transport and Gas Turbine Engines. That's where they trained us. It was the only department in the country that trained students, specialists specifically for small and modest gas turbine engines, for the development of small and modest gas turbine engines for transport. True, those were different gas turbine engines in those days. That was the last century. They were gas turbine engines for transport with a mechanical transmission. There were no high-speed electric generators, the kind that are already present today. These were significantly more complex gas turbine engines, and yet they showed truly remarkable and good results when installed on one or another kind of ground transport.
That engine standing behind you right now, is it one of those engines? Where was it used?
This engine, as far as I remember, yes. So this is the engine. Just a moment, please. This is the engine. This is the first version. So the first version of a prototype unit of an engine for a tank engine. It was around 400 horsepower, that engine. So this engine reproduces the first version, one of the first versions, somewhere around the 1960s of the last century. It had no recuperator, and so it consumed a great deal of fuel. But still, it allowed a certain field of knowledge to be expanded. After that, gas turbine development, transport gas turbine development, moved toward developing gas turbine engines with a recuperator. Because only such engines, the gas turbine kind, could compete in fuel economy with internal combustion engines, including gasoline engines and diesels as well.
To explain briefly what a microturbine is, it's the same kind of engine as the internal combustion engine that sits in a car. Fuel is fed into it, the fuel is burned, it expands, it does a certain amount of work, and then that mechanical work in the engines behind you, the kind they taught and built at the Polytechnic, was turned into wheel traction.
Exactly right.
So not the turbines on planes that make jet thrust.
Exactly, yes, all correct.
Yes, geared to producing mechanical work. And why microturbines?
Quite a few people who heard about this were surprised by such a name. It's because gas turbines took over the markets and areas of application where the power of gas turbines runs to hundreds of thousands of horsepower, even more. If they're stationary engines, then the power is very large. And so, in general, it became settled that gas turbine engines up to 1,000 kilowatts were informally decided to be called microturbines. Because what's 1,000 kilowatts versus 100,000 kilowatts? It's almost nothing, just tiny micropowers. That's one thing. Without a doubt this mattered, but it also mattered that these microturbines no longer turned a car's wheels, no longer produced any motion, no longer drove the rotation of a car's wheels. Instead, they turned high-speed electric generators. So this transition, this application of microturbines, that is, small gas turbine engines, was made somewhere in the late 1990s. Essentially, this was connected with the appearance of high-speed electric generators, highly efficient, high-speed, up to 100,000 revolutions per minute and even more. And these electric generators, on top of being highly efficient and high-speed, were, as a result, small in size and mass. And as a result, they were very well suited for driving gas turbine engines, whose output shaft turns at a very high rotational speed. That is, in this case, these electric generators with a high rotational speed are very convenient to drive with a gas turbine without any reduction gearbox. Essentially, this very joining of gas turbines, small gas turbines with a high-speed electric generator is, in essence, what they call microturbines.
You've already mentioned another element, the recuperator. Yes, and I'd add it to this whole setup for clarity. There's a turbine that burns fuel and creates rotation. There's a generator that spins, which is the whole point of the turbine, and a special heat exchanger, the recuperator, that raises the system's efficiency.
Yes, exactly, that's right. The point is this: huge gas turbine engines have huge bladed machines which have high efficiency, and those big gas turbine engines work at high air pressure ratios. And in that case, a recuperator is not required to reach that high efficiency. The recuperator is needed precisely to achieve high efficiency in gas turbine engines of low power. At low power, the air pressure ratio in microturbines is small, and if you made it large, the bladed machine, in this case the compressor that compresses the air, would become very small, and as a consequence, the whole thing would have very low efficiency. To compensate for this low efficiency of the small bladed machines and the low efficiency of the small dimension microturbine, the idea arose to install a recuperator. What does the recuperator do? The recuperator takes heat from the exhaust gas. That is, the exhaust gas is blown through this recuperator, and it heats this recuperator. And in parallel with the exhaust gas that is blown through this recuperator, there also passes the air that has been compressed in the microturbine by the compressor. So before the combustion chamber, this air enters the recuperator, where it is heated ahead of the combustion chamber by the heat of the exhaust gases, the outgoing gases. And as a result, in the combustion chamber, you now have to burn less fuel in order to heat the air up to the required temperature, say 1000 degrees Celsius. And as a result, efficiency rises very seriously. If the recuperator is a good one, then by 2 or more times compared with a gas turbine without a recuperator. As of today, the concept of a microturbine necessarily includes, in addition to the electric generator, a recuperator as well. That is, a microturbine is a gas turbine equipped with a recuperator.
And in the Soviet Union, they were already made.
In the Soviet Union, yes. Actually, regarding what there was in the Soviet Union, let me allow myself a little bit of history. Yes, in the Soviet Union, they were actually not produced, but rather developed. Not everywhere, but there were some very interesting places, very interesting products, very interesting research was carried out. In particular, starting from the 1960s, the Soviet Union tried to create a transport gas turbine engine, mainly for trucks, for military vehicles, 8-wheeled armored personnel carriers, and so forth. They tried to create one. This took place somewhere in the Soviet Union. It was happening at Nami. I'm afraid I might be telling it wrong. In 4 or in 3 places, the Yaroslavl plant and a third plant, Ano 4. The third place is the Gorky automobile plant, and the fourth place is Chelyabinsk. In Chelyabinsk, the Turbina Design Bureau, that is where they tried to create a gas turbine for a tank. Well, in particular, what is currently behind me comes precisely from there. It is essentially Chelyabinsk's first attempt, their first try. So the greatest successes were. But as you can see, the engine standing behind me is an engine without a recuperator. And naturally, from such an engine, there was no positive, serious result. The greatest results were achieved in developing a highly efficient gas turbine, a small one for transport, at the Gorky automobile plant. There they created prototypes, mainly around 400 horsepower. They were tested on the Mazis, on the Kraz, the Kremenchug automobile plant truck, the Krazi. These are all big multi-ton trucks, including the Kamaz as well, and on military vehicles, the 8-wheeled armored personnel carrier. Somewhere around the late 1980s, there were very successful tests of these engines on the Bryansk multi-axle vehicle, a missile carrier essentially, the Soviet 8-wheeled Bryansk vehicle. Their comparative tests were conducted, comparative tests of this Bryansk vehicle, the Bryansk chassis, with a diesel and with the gas turbine engine of the Gorky automobile plant, with a recuperator, of course, and the results showed a very positive thing. The main problem of the gas turbine is high fuel consumption, that is, a disadvantage in fuel consumption. In these tests, roughly equal road fuel consumption was obtained, average road fuel consumption. The Bryansk vehicle with the gas turbine engine of the Gorky automobile plant and with a diesel. The diesel, there were 2 variants. One was a Barnell diesel, and the second variant was 2 Kamazes. 200 horsepower each, I believe. There was 1 gas turbine engine of the Gorky automobile plant, roughly equal fuel consumption, yet the speed obtained was 30% higher than the average. Very easy starting, without any preheating in wintertime. The tests, by the way, ran in winter at minus 10 to 20 degrees Celsius. The gas turbine started very easily, without any preheating. This made a very great impression on the testers and the representatives of the Bryansk plant. Besides that, during the tests, a very interesting result was obtained. This test was not conducted on purpose. It was obtained by accident. Namely, the chassis of the Bryansk plant, the 8-wheeled one with a diesel, got stuck in meter-deep snow. And this diesel chassis was pulled out of the meter-deep snow by the very same chassis, but already with a gas turbine engine. This again made a very great impression on the testers. I have told you very little, but on the other hand, also very much. The only trouble is that the perestroika that followed essentially put an end to these developments, because our ministry, our government, stopped funding anything, any new developments, even though they were essentially already on the verge of completion. And back then, the central body was the Central Committee of the Communist Party. Even at the level of the Central Committee of the Communist Party of the Soviet Union, a decision was made to bring those Gorky automobile plant engines to industrial production. But I repeat, perestroika in the 1990s killed it all off, the whole gas turbine field. Honestly, not only the gas turbine field, but a great many other interesting fields that were being developed and researched in the Soviet Union.
How fortunate that there remain specialists who can now, so to speak, revive all of this, possessing the knowledge of the past and the tools of the present. And could you let us in on a little secret? For you, after all, this is a family affair, working on microturbines.
Well, on the whole, yes, you are absolutely right. So, at the Gorky automobile plant, the chief designer under whose leadership the gas turbine engines were created was my father, Veniamin Matveyevich Kostyukov. By the will of fate, I picked up the banner in particular. Despite that collapse of research work and of work in general that took place in the Soviet Union, the results of that work, the drawings, the studies, the research findings, the reports, the gas turbine engine samples themselves, all of it we managed to transfer to Moscow Polytechnic University, to the Department of Transport and Gas Turbine Engines, which I became head of after some time. After that, together with the department, we tried with all our strength to preserve and develop this field. And in fact, on the whole, it worked out. Somewhere around the early 2000s, the Salyut plant began to take an interest in our engines. And a division of the Salyut plant, the Salyut aviation plant, was set up at the department in order to begin work on a deep modernization of the Gorky automobile plant gas turbine engines. Essentially, this supported the department, made it possible to continue the work, and most importantly, to pass on the knowledge of designing gas turbine engines to a very large number of students. In particular, as of today, the gas turbine unit or microturbine unit that is being designed at AERONOVA is essentially designed in part by graduates of the Department of Transport and Gas Turbine Engines.
One would think the unit is fairly complex, and that some large design bureau ought to be working on it. But right now you have around 10 people on your team. I'd like to ask, how have modern design methods helped to simplify or speed all this up?
A very good question, Without a doubt, modern meta-design has a very strong influence on the speed of design. But beyond that, the design speed of the gas turbine engine at AERONOVA was influenced, apart from modern technologies, precisely by the developments that preceded the work at AERONOVA, namely the joint work with the Gorky automobile plant and the work that was carried out at the department. Essentially, the department worked for a fairly long time precisely on a gas turbine engine of this size class, on the order of 300 kilowatts. So, but without a doubt, high technology and above all computational technology. Nowadays, anything you like, any flow, any combustion that occurs and takes place there in the gas turbine, in the bladed machine spinning at enormous speed, in the combustion chamber where flow, combustion, mixing and admixing occur, in the recuperator where the most complex thermal hydraulic processes occur, where heat is transferred from the exhaust gases to the compressed air in the gas turbine. Today, all of this is already computed using existing simulation software packages, and very accurately at that. Very accurately, though of course not with 100% precision, but at the very least 90% of it can be reliably calculated, depending of course on the task and on how complex that task is. We were already working with these programs, these software packages, back in the early 2000s and even in the 1990s. Thanks to the fact that the gas turbine engine department at the Gorky automobile plant gave our department a great deal of help. In those days, the Gorky automobile plant had the means, and not merely had the means, but actually bought modern computational software packages, which we essentially relied on, and most importantly, we learned the work from them, which matters a great deal.
Viewers can see this compressor wheel right now. I know that it was tested earlier. And when you named 90% accuracy, were you relying on calculation results checked against real physical tests?
Of course, without a doubt. But at the same time, it should be noted not only against these tests, but against tests that other researchers carried out as well, ones that were published. We carried out validation of how these packages are used across a variety of tasks. For the compressor, for the flow within the compressor, for the flow within the turbine, there are particular features everywhere. Each task has its own particular features, and those features were taken from the research conducted, or more concretely from the validation, essentially, of these computational packages for the task under consideration.
I would like to raise a question. Why microturbines in the first place? Why? Why do we need them? Oh, how are they better? Why are they needed now? And where can they be applied? It seems like such a complex product that, in order to both design it and begin producing it, you need an enormous amount of effort, knowledge, and the experience of several generations accumulated and handed down. Yet it seems fine now without it. Everything moves, drives, works. Or not fine? Sorry for these amateur questions. I know the answer is Andrey Veniaminovich, but I'd like to unpack this topic more.
Actually, that is a perfectly valid question. So, in this case, I simply shrug my shoulders and tense up a little, because the question is a very large one and is not so easily unpacked. Even so, the following can be said. Small microturbines, which I have already touched on a little, people tried to create, including for transport and not only for transport. They tried to create them as far back as the early 1960s of the last century, even earlier than that. And this is no accident, quite unequivocally so. How much effort, how much money was spent all over the world, in Europe, in the States, and naturally in the Soviet Union. Although in the Soviet Union, as it happens, not all that much. But on the whole, enormous research was carried out, and it continues to be carried out. The contours of the future gas turbine are being felt out in keeping with the development of today's technologies. Let me simply give you an example of what I have in mind. I told you about the transport gas turbines that were intended for use in vehicles with a mechanical transmission. That is, these gas turbines did not turn a generator, not an electric generator, but the wheels of the car through a gearbox, through a clutch, and so on. Back then, all these engines, the gas turbine engines, besides the compressor, the turbine, the rotating rotor, the recuperator, and the combustion chamber, also had a whole host of additional parts to handle the entire complexity of the task of turning the wheels. A reduction gearbox was needed, a powerful, strong reduction gearbox that would step down the speed from the gas turbine, which spins at an enormous rate, 30,000 revolutions per minute, to the rotational speed required for transmission into the gearbox. Say a diesel gearbox operates at 2,500 revolutions per minute. So you get a very powerful, very large reduction gearbox. Naturally, it requires oil, and it adds quite a serious amount of mass to the gas turbine unit. On top of that, there was another thing. The variable nozzle assembly ahead of the power turbine, which made it possible to improve the dynamics of a vehicle equipped with a gas turbine. What exactly is it, this swiveling assembly, this nozzle assembly? These are swiveling fixed vanes that direct the flow onto the gas turbine at the required angle. And since this is a swiveling nozzle assembly, it can change that direction. It can speed the gas turbine up, it can slow the gas turbine down, and it can even start turning that gas turbine in the opposite direction. This naturally made it possible to significantly improve the dynamics of a transport gas turbine, but at the same time, it significantly complicated this gas turbine, complicating it, making it heavier, and making it more expensive. And so back in those days, the gas turbine, compared to the internal combustion engine, was, for the reasons just listed, somewhat more complex, substantially more complex than the internal combustion engine. Today we have a rotating high-speed rotor that turns a high-speed generator, and there are no large reduction gearboxes and no swiveling variable nozzle assemblies at all. None of that exists anymore. That is, thanks to the development of technology, and more specifically the development of high-speed generators, we obtained a simple, simplified, substantially simplified gas turbine, namely the microturbine, a small gas turbine engine. Today, such a gas turbine, in keeping with the technologies available now, and I already spoke about the generator, makes it possible to substantially simplify this gas turbine unit, to improve it, to raise its parameters, its effectiveness, its efficiency, to reduce its mass and dimensions. And it has turned out to be very attractive today for a number of users. Take, for example, the American microturbine. They tried installing it on transport, on a bus, on marine transport, on trolley buses, and among other things, they used it as a power unit to generate cheap electricity and heat for houses, settlements, supermarkets, and so on. That is, the range of applications turned out to be very wide, both this way and that. What emerged was a multi-purpose microturbine unit, which is naturally very attractive. You can use it here and here and here. It turns out to be a quite significant market. But besides that, the gas turbine is appealing thanks to its well-known properties, namely its multi-fuel capability. It easily runs on practically anything that burns: gas, alcohols, petroleum fuel, kerosene, gasoline, diesel fuel. It can run on heavy fuel oil as well, but here there are certain complications. In that case, it will not operate efficiently. You will need to lower the maximum temperature, otherwise the gas turbine blades will quickly deteriorate and corrode.
Environmental requirements. As I understand it, today's environmental requirements for exhaust emissions also, at the very least, put the microturbine.
Exactly, that's right, yes, without a doubt. Today, as is well known, essentially these processes had been going on somewhere already starting from the 1980s and even a little earlier. Environmental performance. Environmental performance was a banner and a requirement, a direction along which power units were being developed. It was essentially a banner of requirements demanding lower toxicity and lower harmful emissions. Today, this is well known. These requirements reach incredible levels and, moreover, demand not just the absence of emissions of oxides of nitrogen and oxides of carbon, but it is also being banned, or at least the measures are moving in that direction, to fully prohibit emissions not only of oxides of carbon, but also of carbon dioxide. In this case, the request is for power units that emit no carbon at all, which, as we know, is tied to the climate.
Because the combustion temperature differs from that of internal combustion engines, in a microturbine it is possible to create conditions in which these harmful oxides do not form at all.
Yes, the gas turbine is good because harmful emissions can be reduced in it, and they are reduced without any additional devices of the kind installed at the exhaust of the familiar internal combustion engines, gasoline and diesel ones. In a gas turbine, you need to do none of this. Additional devices are not needed. It emits very few oxides of nitrogen. This is due to the fact that in modern combustion chambers, the maximum temperature does not exceed 1500 degrees Celsius, and it is well known that the formation of oxides of nitrogen is thermal in nature, and oxides of nitrogen are mostly formed at combustion temperatures above 1500 degrees Celsius. So then, if you make the combustion temperature lower, in that case you can achieve a practically complete absence of oxides of nitrogen. This can be done in gas turbines, but it is utterly impossible to do in an internal combustion engine. Because of this, the gas turbine potentially possesses, in principle, a level of environmental performance that is unattainable in internal combustion engines.
Yes, and again, the lack of extra units strongly affects the design's total weight. And so we smoothly arrive here. Maximum weight efficiency. The highest speed generators come into play, ones where 30 kilowatts can be fit into something the size of a fist and weighing 3 kilograms. So basically, this is a quality that is required for aviation. And the entire trend of modern electric aviation most likely crystallizes precisely around microturbines that generate electricity on board, which is then used by electric motors, again modern and highly efficient ones, to turn the propellers, which is broadly what we are engaged in here. Andrey Veniaminovich is creating a microturbine of 300 kilowatts of electrical output power, with an enormous background behind him, both his own and the Kostyukov dynasty, which created all of this work. And the microturbine that we are getting now will be used first and foremost in airships. This is what we are engaged in at the company AERONOVA. For understanding, there is, for example, a diesel power unit of 300 kilowatts of electrical output power. And here's our microturbine of 300 kilowatts electrical output. At a comparably equal efficiency and fuel efficiency, we can compare the weight of these two units.
The weight of the gas turbine, the diesel naturally falls substantially short in mass, being substantially greater in mass compared to the gas turbine. Even if the gas turbine is weighed down by a recuperator and ends up with an engine efficiency close to that of a diesel, even in that case, the diesel loses significantly in mass compared to a gas turbine engine with a recuperator. It's called a gas turbine, a regenerative gas turbine. I said that just in case because, well, it's clear anyway. So then by an order of magnitude, well, not by an order of magnitude, but by several times, roughly several times, in terms of mass and maintenance, the service life of a gas turbine is significantly greater than that of a diesel, significantly greater by several times. Specifically up to overhaul, a diesel has on the order of 20,000 hours, while a modern gas turbine has up to 60,000 hours of service life to major overhaul, that is, to the big repair. This is important from the standpoint of operating costs and of comparing the application of a gas turbine with a diesel power unit.
So engine efficiency is comparable. A diesel now is around 45.
A bit less.
42?
At roughly that power, somewhere around 40%.
And that microturbine we are specifically developing right now, its efficiency is a bit lower, isn't it?
Yes, our gas turbine is still a bit lower. It has on the order of 37% efficiency, but potentially we plan to raise this efficiency, above all not by complicating the structural layout of the gas turbine, although that path exists as well. As of today, microturbines of about 400 kilowatts have an efficiency of 42 to 43%. Such microturbines exist in the world, but they are more complex. That is, they have a complex twin-shaft structural layout, and there is an additional element present in such a gas turbine, and that is a little unsuitable for our transport application and above all our aviation application. We can even afford to lose a little in engine efficiency, But at the same time, one of our principal requirements is mass and dimensions, but above all mass, of course. Therefore, in this case, we will quite unequivocally win the competitive battle against the diesel with our gas turbine, our microturbine of 300 kilowatts.
And the sound? The noise? We're all used to a turbine being the thing on a plane you can't even walk past. It whistles and roars, even aboard, where it's far away, and outside while you're inside it's noisy. But a microturbine is a different product. What's the noise level there? Do tell.
Yes, of course. This is yet another positive property, not of a gas turbine engine, but precisely of a microturbine, which has a recuperator in its structural layout. A recuperator is a porous structure, a porous volume through which the exhaust gas passes. As the exhaust gas passes through this porous volume, the pulsations and noise within it are damped very strongly, and as a result, the noise of a gas turbine engine with a recuperator, that is, a microturbine, is substantially lower than the noise of internal combustion engines. And correspondingly, as for noise, take the example that Fyodor gave, the noise of aircraft engines. Most of us have probably flown. In fact, I think everyone has flown on airplanes. The noise is quite loud, frankly speaking, on large gas turbine engines, but they have no recuperator. The recuperator damps the noise very strongly at the inlet. Besides the recuperator, without a doubt, since the microturbine also has ground applications, an air filter is placed in front of it, and a recuperator is placed at the outlet of this gas turbine engine. And these two porous elements, the air filter at the inlet and the recuperator at the outlet, unlike an aircraft engine which has neither an air filter at the inlet nor a recuperator, produce substantially less noise. Actually, it is a fairly quiet whistle, a high-frequency noise from the gas turbine. This noise is well known to be easily suppressed. We can enclose this gas turbine in some kind of thermal insulation material, and the noise will be reduced very strongly on top of that. We can enclose this gas turbine very seriously because the casing of the gas turbine does not need to be cooled, unlike internal combustion engines. Naturally, when we enclose this gas turbine in a sound insulating mat, we also thermally insulate it. But for a gas turbine, there is nothing wrong with that, owing to the fact that its outer casings are not cooled, unlike internal combustion engines. So on the whole, a gas turbine is not only lower in noise than internal combustion engines, but it also has potential. If desired, this noise can be reduced even further, very strongly, in automobiles.
In automobiles, for example, from the same Gorky automobile plant, was the noise level while sitting in the cab comparable to that of internal combustion engines?
Substantially less. During the testing of the car with gas turbines, the driver complained about one thing. After some time, he would start falling asleep. He did not need to shift gears while driving because the twin-shaft gas turbine had wonderful torque. He simply pressed the gas pedal and the gas turbine ran, and the car went uphill or downhill. It did not matter. There was no need to shift gears. The gear was shifted by the driver in only one case during the start. And after that, he simply forgot that he needed to shift gears. Shifting gears in this case affected only one thing, the fuel consumption, but the dynamics of the car, not at all. But the driver naturally was not always concerned about fuel consumption. He was concerned only that the car ran at the required speed and climbed the hill and went back down the hill. To carry out this process, one could use only the pedal with no need to shift anything. So essentially, an automatic transmission without an automatic transmission. As for noise, I already said that the noise of a gas turbine is very small, low to begin with. But when installed under the hood of the car, this noise was further reduced very strongly and had a sleep-inducing effect on the driver. Probably so, yes.
You just touched on this idea of a gearbox without a gearbox, and surely a natural question follows. Is the efficiency really that good at all frequencies, at all rotational speeds, under all the loads? Or when a load appears or when it falls away?
The question is clear, completely obvious. For example, a diesel engine has efficiency up to 50%, and reducing power by 50% practically does not lower the efficiency. A gas turbine without a recuperator sees its fuel consumption grow impossibly high at partial operating modes. This is exactly the problem the T-80 tank ran into, since it was fitted with gas turbine engines that had no recuperator. That engine gave the tank wonderful qualities, namely its dynamics, owing to its small weight and dimensions. And it provided fairly simple replacement. You don't need to bring in a lifting crane to haul it out of there, this gas turbine. But at the partial modes, where the tank mostly works, yes, fuel use came out very high. But for a tank, that is not always important. This application is still considered promising even today. Production of these gas turbine engines for the T-80 tank has, as is well known, now been resumed at the Kaluga engine plant. An engine with a recuperator has quite a decent fuel consumption at partial operating modes, and there is no longer such ugliness as with a gas turbine of the simplest layout without a recuperator. Besides that, fitting an electric generator onto the gas turbine, along with additional control of this generator, allows the gas turbine to run with high efficiency even at partial operating modes, at partial loads. This, I repeat, comes down to two reasons. The first is fitting a recuperator. The second reason is fitting an electric generator. That is, we do not connect the turbine shaft to the wheels of the car. Instead, we connect it to an electric generator and control it, so that is additional control as well. And all of this leads to the problem of high consumption at the microturbines' partial operating modes being largely eliminated.
What I'd like to note is the low weight, the low noise, even a smaller number of parts compared with an internal combustion engine, and far fewer at that. Sufficient fuel efficiency and a high waste heat value. I am listing the very advantages for which the microturbine was chosen for airship building as its main power unit. We'll discuss the waste heat value in airships a little later. The advantages are, so to speak, enormous. But what about the cost after all? In 95% of cases back, a person thinks a turbine is far more expensive than an internal combustion engine.
Yes, a turbine is far more expensive, but I think I already spoke about this. Then again, maybe not. All the more reason to say it. A gas microturbine, as of today, is more expensive than a power unit with an internal combustion engine. This is due to the fact that gas microturbines today are produced practically one piece at a time. There are no series. There are series, but they are very small. And in that case, naturally, comparing the cost of a gas turbine under single unit production with the cost of an internal combustion engine that has mass production, that is, thousands of pieces, clearly turns out not in the gas turbine's favor. Then the product naturally comes out much more expensive. We are, of course, counting on the fact that our gas turbines, which we are building first and foremost for the airship, will have other purposes as well. That is, in essence, we are creating a multi-purpose turbine today. And in that case, we plan to set up production that is no longer single unit but serial, since we are counting on a large market. And in that case, the cost of our product, of our microturbine, should already be significantly closer to the cost of a power unit with an internal combustion engine. Just in case, let me add, the cost of a complex gas turbine that drives the wheels on a vehicle was calculated, worked out very many times, and by very strong research institutes back in the 1980s. Otherwise, this work would not have continued. The research and the attempts to install these gas turbines on transport would have ceased had there been such an unfavorable cost ratio, including between the gas turbine and the internal combustion engine. I roughly remember one of the reports of a Central Research Institute of the Soviet Union. I cannot tell you its name right now, unfortunately, but I remember that report perfectly. And later on, all the manufacturers of microturbines who tried in the Soviet Union to build these microturbines for transport relied on it. So, this institute gave the following result. With comparable production of a complex gas turbine versus an internal combustion engine, a diesel engine in particular, and the gas turbine was being developed specifically to replace the diesel, owing to the fact that it used cheap diesel fuel. Such a complex gas turbine engine, it was estimated, would be roughly 10% more expensive at comparable production volumes than the diesel. I repeat, as of today, we plan to substantially expand the market of application for our power unit, and as a consequence, to set up serial production of our multi-purpose power unit.
Yes, I would also like to tell a little more. After all, we communicate with many players in the industry, and just recently we once again interacted with our Chinese colleagues. They received a task, so to speak, from those who plan technical progress for the further future, to create a turbine of the same power for electric aviation. They took a European one and modified it slightly. Theirs is a twin-shaft configuration, so they rigged up an electric generator to it and so on, and they were estimating its cost for electric aviation. And it came to a fairly high order of prices, fully matching aviation, roughly speaking. Standards, trends, yes. But they have a second calculation. When, from the aviation ones, they invest further into the actual mass production of these turbines and then adapt them for distributed energy, for electricity generation somewhere on site where it is required, then with mass output their cost directly. That is, it comes one-to-one with units of the same power class, only diesel ones, for example. The price comes out one-to-one there. But they gain a great deal in materials, in service life, in many things. And their vector is set on this. They have already calculated it all unambiguously and will certainly do all of it superbly. And they were counting the market in thousands per month, just their own internal one, which will not be covered at such a pace in the coming decades, if not longer. But we also spoke with them about the external market and tried to assess it together. They said you cannot even try or make the effort. If we learn to mass produce the microturbine as a power unit, they say, the demand for it will be colossal, which I believe in and which I wish for all of us to achieve together. And this whole conversation was only about one size, from 300 kilowatts up. There are also ones slightly larger or much, much smaller. And the market, all in all, I want to say, is boundless. There. All the advantages of the microturbine, namely its compactness, its weight efficiency, and so on, will allow us in the future to create products of such consumer qualities that we cannot even imagine right now. Andrey Veniaminovich periodically tells this story about how microturbines were being developed around the world and perhaps still are being developed, behind closed curtains. Ultra-compact, ultra-small, running at very high revolutions. as power units for those very same robots. Andrey Veniaminovich, what power levels were discussed there?
These are small powers. This kind of work was being done very actively in the early 2000s, in the late 1990s. These were power levels somewhere around half a kilowatt, specifically for the application for powering robots of military significance, above all humanoid robots. In short, robot soldiers that would be powered by it, carrying such a small power unit in a backpack, and would move thanks to it and carry out bad military actions or good ones. In those days, batteries were not yet so highly developed, and the energy capacity of batteries was very small. So the development and creation of such a microturbine power unit was considered very promising, above all for robots of military purpose. As of today, such units have surely not dropped off the agenda either, quite unambiguously. These are very small, very simple gas turbines with a very high rotation speed. That is, gas turbine engines plus an electric generator. The speeds being developed reached 1 million revolutions per minute and more. I think there were even figures up to 1.5 million. At least in the press, in scientific articles, those were exactly the figures reported. As of today, I repeat, all of this has surely not dropped off the agenda, quite unambiguously. It has only been supplemented by the availability of new energy-dense batteries.
When I studied this question on my own, if memory serves, and by my impression it really did seem so, the mass output of a small microturbine running on hydrogen, for example, can be higher than that of modern lithium batteries that can store the same power. The unit can be lighter.
Yes, of course, it's lighter naturally. That is exactly why batteries are not used in aviation. They are not installed. True, there are such attempts. It was reported quite recently. In small aviation, they mostly use power units, either turbine ones or ones based on internal combustion engines. As of today, they still win out over modern batteries on mass and on energy capacity.
And yes, I'd also like to say a bit about the markets. Actually, we should cover airships. We do build airships. We have two 300 kilowatt microturbines. In our next craft, the Nova 8 of 8,000 cubic meters, they should already be installed, running full power, making power, turning props. Airships fly. The bigger the airship, the more microturbines. The power level will hardly increase, 400 kilowatts at most. There'll just be more of them. We build airships. Would you like to see how they fly? Scan the QR code. Sign up, come over. In Voskresensk, we fly small ones. They're still electric, no microturbines. But microturbines are a really fascinating story. There's so much I'd love to tell you and clear up. So, they're not only used in aviation. I know there's a very big trend right now in China, and not only in China, around hybrid cars. Electric cars are all great and cool, but right now the series hybrid has proven itself better. Where something generates electricity, there's a small buffer battery, and there are electric motors that draw the electricity and spin the wheels. The car moves, and this approach has proven itself now. And I know for sure that China plans to replace these internal combustion engines with turbines. In Russia, there's even such a movement. There are a great many requests around this. And these 50 kilowatt turbines, and practically by the millions. Everyone hopes to ride this market too.
Yes, so today transport is being electrified by leaps and bounds. That is, it's switching to electric transmission with storage batteries. But at the same time, for a number of reasons, these storage batteries continue to be, and not only continue, but people try with all their might to be equipped with so-called range extenders. Essentially, in that case, we get a hybrid power unit. But this car with a range extender, that is, with a little power plant, with a small power plant, lets the electric car driver feel considerably more confident, because after 300 kilometers or after however far his batteries run down, he might not find that charging station in that case. But a fuel station, one that fills the fuel tanks, he'll definitely find. For this reason, at least for now, the creation of electric cars is combined with intensified work on installing on them an additional power unit, an additional power plant, that is, a range extender. Yes, this range extender in a microturbine form compared with a piston form will have a significant advantage, a significant merit. This is connected above all with mass, with size, but without doubt with noise. Yes, you don't want to get extra noise. On an electric car, you don't want extra noise from a power unit based on an internal combustion engine. You don't want extra shaking, right? This power unit with a piston engine will shake. A gas turbine engine doesn't vibrate at all during its operation. Your shaking and vibration are noise, and it'll all be transmitted to the car body. And a gas turbine has none of that. Besides that, the gas turbine is multi-fuel and can use any fuel, and most important, cheap fuel, propane, butane gas, for instance, with no problem. A diesel can't use propane, butane at all. Here, gas turbines absolutely clearly appear considerably preferable in this application. Multi-fuel capability, mass, fairly high efficiency, long service life, low mass, long service life. The environment, again, no odor at all, nothing in the exhaust. A microturbine won't create these troubles for you, unlike an internal combustion engine. Because of this, work on developing microturbine range extenders is being actively pursued around the world. We have these developments too, microturbines of 50 kilowatts and 30 kilowatts. We worked in this direction back at Moscow Polytechnic University, and the work was even carried out jointly with the Chinese Tsinghua University. The only thing is that since it was, after all, a university, the work was not carried through to building the hardware. We designed this power unit and designed individual components. And we didn't just design certain components, we also tested them, in particular the recuperator. We had a special recuperator. It gave a very high degree of regeneration while having small dimensions and mass. As a matter of fact, this work was called a microturbine with an ultra-high degree of regeneration. That is, with an ultra-high efficiency of the recuperator. We manufactured and tested this recuperator and manufactured and tested the combustion chamber, a low-emission combustion chamber. It showed very good results. Here, as a matter of fact, a very serious foundation has been laid. Looking ahead, we also intend to take up this direction additionally. But here it should be noted that it is precisely the small dimensions and low power that make it possible to try using high-temperature ceramic in such a microturbine. This will make it possible to raise efficiency and reduce the dimensions and mass of the microturbine. And in this direction, we are also working together with firms engaged in the development and research of high-temperature ceramic. That's probably it. I think I've covered this section.
It's not only the heat-resistant wheels that can be ceramic, but also a fairly large range of other parts. And ceramic, as we know, is many times simpler and lighter than steel, and a whole lot of interesting things. There the temperature rises and efficiency rises sharply because of that. And the promising small ceramic turbines will, of course, have properties that are quite amusing for an ordinary user. This is the ratio, roughly speaking, of mass and size to the power produced. They will be utterly tiny, yet the amount of electricity will be quite large. As I said again, modern electric generators the size of a fist can easily put out 30 kilowatts of electrical power. Try to Google how much it puts out. What size? Some classic 30 kilowatt electric generator. In short, it'll all become clear there. Coming back to the airships, there's another very amusing story too. Andrey Veniaminovich has a long history of work on microturbines. And our airship builders with whom we now build airships and also have great experience. And what was funny was that they met, roughly speaking, here at our company, even though they had already been collaborating beforehand on the use of microturbines, specifically in airships. So microturbines have, and now once again we're all working on this together. A microturbine has this nice property. It generates a large volume of fairly cool air. How much is it there? Somewhere around 200 degrees, 250, 300?
Let me correct that a little. They generate a large flow of heated gas, exhaust gas, which is essentially close to air in its cleanliness. That is, there won't be any oil, none of those nasty things in there. A fairly large quantity. I'm listening, go on.
Yes, and this is measured in cubic meters per second.
2 cubic meters per second, yes.
2 cubic meters per second heated to
250 to 260 degrees Celsius.
And what outlet temperatures does a piston engine give?
At the outlet, it has a temperature of 600 degrees Celsius. A diesel engine is a bit lower. A gasoline engine in some operating modes, its temperature even climbs up to 900 degrees Celsius.
The temperature is high, but the volume of air is small. And here the volume of air is colossal and the temperature is low, which lets us use precisely these exhaust gases in airships for clear and useful functions, one of which is everyone asks about anti-icing systems. And now, how do you heat that envelope? So when you have such a quantity of fairly low temperature air, you can use it very well and efficiently to solve this task. If this air were too hot, you'd have to cool it more or such, since airship material can't withstand such temperatures. And here the temperature of the exhaust gas is fairly low. That's one of the systems. And even more important, though icing is also very important, is the buoyancy control system. By heating, I won't quote the exact figures right now, but these 2 units of 300 kilowatts each are quite enough for a volume of, for example, 8,000 cubic meters. And it's enough, roughly speaking, to switch a damper and send this warm air wherever it needs to go, and to increase, for example, the airship's lift by around 30% easily. And the buoyancy control system on airships of the classic type, for example, is one of those really thorny questions. If it's a transport cargo airship that needs to release its load, where does it put that excess buoyancy? And the methods will always be combined. They won't rely solely on heating and cooling the lifting gas. This task will also be addressed by additional methods. Well, the main solver for this task is precisely the calorific output of the turbine. So, roughly speaking, we raise its overall efficiency by putting that heat to good use. And we'll certainly never freeze if we fly the airship somewhere cold. Let's be quick, Andrey Veniaminovich. I think we've been sitting here quite long enough. People may already be tired of our, I hope, interesting stories. So let's run through it. What stage is the work on the microturbine we're building actually at right now? What work's done and what's left to do?
Work on our microturbine has moved into the manufacturing stage. As of today, we're already manufacturing the main turbocompressor components: bladed machines, compressors, turbines, rotor bearings, and shafts, of course. We plan for these parts to be ready within a few months. Naturally, production of other parts has also started, the combustion chamber and the recuperator. Although the recuperator will still require developing a manufacturing technology that doesn't exist in Russia today and never has. Creating the technology for a stationary recuperator, compact with high effectiveness, with high efficiency, is a technology we'll have to develop ourselves. Well, our plan is that while the remaining parts are being manufactured, we'll develop the technology to design and build the recuperator and then build it. That will take not a few months, but somewhat longer. Nevertheless, the recuperator won't delay developing this new technology, nor delay the manufacturing and the experimental prototype as a whole.
We still have to build an assembly and test shop where we'll carry out, roughly speaking, the assembly, commissioning and fine-tuning of the turbine itself, where, for instance, the recuperator modules will first be tested separately than the complete recuperator. Then assembly, startup and testing of the entire microturbine fully assembled, for example with a water break. Then in combination with the generator as well. By the way, our generator is ready. Our generator has been tested. The generator is waiting for the birth of the turbine with its recuperator. It's already in the process of being born right now. Some of the parts are still being purchased. There, for example, there are pumps, an oil pump too, and radiators, for instance. That same generator needs cooling, so it ends up being oil-cooled there. So that's a small production space, you see, for testing our first turbines, and we manufacture them 2 units at a time at first. So by the end of this year, we need to form a staff for the team of assemblers and testers, and fully staff it. And interesting times will begin.
Interesting times will begin, very interesting tests and fine-tuning, if it's needed, of course. We will quite unambiguously learn something new from the turbine we've built during the tests, and that won't necessarily be anything unpleasant. I hope just the opposite, something new and pleasant, something that will pleasantly surprise us. But there's a lot of work ahead, and strictly speaking, aside from conducting the tests and creating the experimental setup, there are no problems here, and there won't be any that take long in time. Right now, we're thinking very actively and searching for premises, thinking through the process of preparing for production, where, how, and when we'll begin creating this. Preparation for production, manufacturing a series of 300 kilowatt microturbine engines.
And regarding the series, what would you like to say? Overall, from the very beginning, I'll repeat myself now, many have heard this, the strategy chosen for the turbines was not to develop products with an infinite number of unknown variables, super modern ones, on incredible technologies with some kind of know-how, designs and so forth, but precisely to design a first prototype that, with a very high degree of probability, would start up, would work, and would show all those parameters and characteristics built into it at the development stage. And they were laid down from the outset in such a way that this very power unit could be applied not only in the airships that we are designing, and what we're designing is an 8,000 cubic meter machine, which is 3 to 4 tons of payload capacity with a flight range of 3 to 4,000 kilometers as well. So basically it's a working machine. We already roughly understand now that to cover the needs of just 2, conditionally 3 major players inside our country alone, 100 of these machines will be needed, and that means a couple hundred microturbines. We could simply roughly close all that demand onto ourselves. But specifically in this version 2, in this corridor of power outputs, this turbine has a fairly large market. Andrey Veniaminovich said that it's like marine transport. In particular for Russia, that's river transport. For example, this is large heavy-wheeled machinery. As I understand it, quarry machinery requires microturbines like these. These are distributed energy systems. These are electric locomotives.
Rail transport as well. In Russia, there are a great many non-electrified railways where the trains, mostly small ones in that case, are pulled by a diesel locomotive using diesel-electric traction. In this case, our microturbines, not just one, we can install them as a cluster, 3 to 4 such power units in a locomotive, and it will still be substantially smaller than a diesel, both in mass and in the size of the diesel used in locomotives. As a consequence, this will quite unambiguously be advantageous, and such a power unit will come out ahead in terms of operating costs, because it can use, for example, cheap fuel, liquefied gas, propane butane. A diesel cannot run on propane butane. A diesel cannot run on methane alone. Some quantity of diesel fuel must always be used together with the methane. A gas turbine, however, can run solely on cheap methane, liquefied gas, or propane butane. As a consequence, in this case, in terms of operating costs, such a power unit will outperform a diesel one. At present, we have a proposal specifically for the use of such a power unit in so-called rail buses. But this is essentially what I was describing. It is a small train used here on non-electrified lines. And here our turbines will quite unambiguously have serious advantages compared with existing diesel trains. Besides that, without doubt, we have already spoken about this, there is electrified transport. And here even a 300 kilowatt microturbine can be used as a range extender if the microturbine unit is mounted on very powerful, large trucks with an electric transmission. Trucks of this kind are being developed and worked on in the form of startups in the United States. We were even offered a chance to take part in such a startup, but unfortunately, or perhaps not unfortunately, the war in Ukraine nonetheless began, and in that case all contacts with the United States and potential joint work were closed off. Well, in a sense, this is probably even good. At least our development will not go off to the United States of America. It'll stay in Russia.
But this placed upon us a certain additional burden of responsibility to bring this development into metal after all. There you go. Which we naturally are trying with all our might to do, and I am sure that success is really not far off at all. You can't have it all and not make it. You'd have to be, though anything may happen. We are moving toward the creation of 2 working prototype microturbines with recuperators, rated at 300 kilowatts. We hope that this year they will be assembled, started up, and tested. And then, roughly speaking, although echoes are already coming in alongside this. So, there are customers for them. The market is clear, roughly speaking, a queue waiting for a miracle. And the closer this miracle, meaning launching prototypes, the more the queue itself opens doors, comes in, knocks. Basically, the closer it all gets, the clearer and clearer it becomes. I'm sure there will be a large enough series to form a full-fledged serial production. There are no technological difficulties whatsoever to be seen in creating the parts of this turbine. Yes, it's high precision, it's serious tolerance grades, it's heat resistant, hard to machine materials, it's precision bearing assemblies. By the way, with the bearings, yes, there are difficulties, including the absence of domestic bearings. Yes, and not only domestic ones, take that very same China, which all our developers are now looking to. China is looking around too. So, Where do we get these bearings? There are questions, but it's all not a problem, so to speak. In the current state of affairs in the 21st century, this is merely a task that can be solved, and they all get solved. Reminder, just in case, our International Space Station flies in orbit. Someone plans to colonize Mars. China travels at over 400 kilometers per hour between its provinces. We have nanometer chips. So, we'll handle the hardware too. There. Friends, I hope it was fun and interesting for you. Not fun, we were a little gloomy somehow, but it'll get merrier. We held this educational webinar for you. I even partly wove in your questions people were writing to me here. And as for mass production, can turbines be produced? Of course they can, and that is the very goal right now for very many states, and not just for us alone. Thanks for your questions, thanks for joining and watching. Thank you, Andrey Veniaminovich, for being who you are and for driving this process forward. An idea flashed through my mind today. So, just one more minute. We have famous people like Glushko, for example, the creator of rocket engines. And these are people who inscribed their first and last names into history. And here's the thing. A microturbine is no simpler than that very same rocket engine. And the feat that Andrey Veniaminovich is accomplishing, creating this turbine, can calmly be placed on the very same level as those celebrated names, and all the more so a microturbine fitted inside an airship. Andrey Veniaminovich, well, there it is, very modestly, of course, but he is making history. So, friends, let's take a moment to feel genuine respect for people capable of such deeds. Get involved where you can, help out. Basically, follow the project and wait for the moment we launch it. And we, for our part, will be covering all of this, showing it and telling you about it. And let me repeat once more. If you'd like to come and get to know us better, there was a QR code during the broadcast. In Voskresensk, at the aviation center, we have 2 small airships standing there. Fully electric, one classic, the other aerodynamic, the so-called hybrid. Sign up, come on over, and I'll personally show and tell you what airships are, why they're important, why they're needed, and if anyone asks questions about the microturbine, I'll answer those too. Andrey Leonidovich, thank you.
Thank you. The one thing I'd like to add is that gas turbines, among other things, are created not by some single person, but by a team. Well, I don't even know. A group of passionate, devoted people. Probably so. Not one person. That's absolutely certain. Thank you. Thank you.
That's all, friends. We'll keep in touch. Bye all.
Thank you. All the best.
AERONOVA is developing a full lineup of aircraft across multiple classes, from lightweight unmanned platforms to heavy airships designed for complex logistics operations, showcasing their capabilities and effectiveness in the modern world. The aircraft lineup will include several prototypes. Among them are the Nova 01 and the Aerolot 01. These aircraft were built specifically to test and put into practice all the modern solutions that the company plans to implement across its future production models. It is my pleasure to introduce our first aircraft, the Nova 01 Airship. It is essentially a dynamically scaled copy of our next model, the Nova 2. We use it to refine and test flight control systems, autopilot functionality, and data collection processes. In the future, an upgraded and further developed version could become a fully standalone product, whether for aerial monitoring missions or advertising applications. Its envelope volume is 130 cubic meters, and its total length is 17 meters. It is capable of carrying up to 20 kilograms of useful payload on board. whether that is specialized equipment or any other type of cargo that needs to be transported. Future modifications of this aircraft could also become a standalone commercial product, serving as an advertising platform or as a dedicated tool for monitoring and surveillance operations. Aerolot 01 is our hybrid version featuring enhanced aerodynamic characteristics. It is an experimental model on which we are also testing new solutions that are unconventional even for next-generation airships, solutions that may well be applied in our upcoming models. In addition to aerostatic lift, this craft also uses aerodynamic lift, which improves its performance across a range of specific tasks and missions where airships can be effectively deployed. Its envelope volume is approximately 190 cubic meters, its total length is 19 meters, and the maximum payload capacity it can carry on board is around 50 kilograms. The lineup also includes the Nova 2 Airship, a craft with an envelope volume of 2,000 cubic meters, capable of carrying 500 kilograms over a range of 500 kilometers. Its passenger version will be designed to accommodate 6 people, including the pilot. Next in the lineup is the Nova 8 Airship with an envelope volume of 8,000 cubic meters. This aircraft will be capable of transporting 19 passengers or up to 4 metric tons of cargo across a range of 3,000 kilometers. Rounding out the lineup is the Nova 35 Airship, a craft of an entirely different class, featuring a rigid hull structure. It will be the very first and smallest rigid hull aircraft that the company is planning to produce and bring to market in the future. This aircraft will be capable of lifting a minimum of 15 metric tons and transporting cargo over thousands of kilometers. The full lineup is designed to address a very large share of the demand that has emerged in today's logistics and freight transportation market. Our next step is the Nova 2 Airship, which is capable of carrying 6 passengers or 500 kilograms of cargo over a distance of 500 kilometers. Thank you all for watching this video. Friends, stay with us. More videos and episodes are coming about how we are reviving airship manufacturing. See you in the next ones.